So we have discussed about this backpropagation algorithm already. Uh, you have seen that basically the learning of a multi-layered perceptron is nothing but some series of steps in a loop. So now I will show you a example, a very simple example, and there basically you will see whatever we are we have seen over here is looking a little bit tough to write the program. It's not really very tough, it's very easy if we use, you know, you can say a form of linear algebra. I don't, you don't worry that you have to, you don't need to understand a lot of things in linear algebra. We will write program with matrix. Let's see. So suppose a situation is something like this. As I told you that in the first step is that initialize the synaptic weights randomly. So we have a say random weight declaration, and according to that we have this set of weights in the multi-layered perceptron where these black levels are actually the bias of the neural network. As I have told you that in my previous video that bias cannot be there in an output layer. That's why only bias is present in the inlet layer and the input layers. And obviously this bias is connected with the inputs. Even bias cannot have any input also, right? Okay, bias fixed value is 1. That's why you see bias is just there, which is affecting the output of the next layer, but it is not taking input from previous layers. That's why this bias is not connected by any synaptic weight from the previous layer. Okay, and you see, assume that there is a set of set of points, and among them one of the points is representing by two features. Okay, the first feature value is 0.2 and second feature value is 0.75. Okay, and if you just write if you put these features in these two neuron and you continue with these different synaptic weights, some arbitrary synaptic weights, and you go through this, you will get y1 is equal to 0.35 and y2 equal to 0.52. Okay, so these are the outputs from the output layer. Fine, and obviously I must have some desired value so that I can start learning, right? So that mean uh, this, suppose we are considering a binary classification problem. Okay, binary classification problem means there will be of only two classes. So one, suppose this particular output, okay, the output of from this output unit is representing class 1, and this one representing for class 2, and how we will, how it's actually, we can show it. We can show in this way, like if the data here is representing, if the data is representing which is a data of class 1, then this part desired value will be 0.99 and d2 will be 0.01. If the data that I am feeding from here is of class 2, then this desired value will become 0.99 and this will become 0.01, suppose. Okay, in this way. So now consider a situation like we are putting some data of class 1. That's why I'm expecting that the desired value over here will be 0.99 and desired value over here will be 0. 0. You know uh, 0.01, but we are getting this 0.35 and 0.52. So these are the errors, right? This is the error. So from here your learning will start. You see, the situation is something like this, and the status of the, you know, is, I mean, the status of the other part of the neural network is something like this. Pattern vector looks something like x1, x2, and bias. These are the three inputs, right? So you can, it can be a simple vector, or you can represent it by an array. Okay, and any other way you can represent, depends on your own programming capability. And the value of this one will be 0.2, 0.75, and plus 1. So I'm some, okay, so 0.2, 0.75, and plus 1, fine. And this is the set of weights. You see, I have 3 cross 3. What does it mean? Why it is 3 cross 3? The reason is that this particular one, always remember, this one in this side, this side represents uh, the next layer, neuron. Okay, and this side represents the current layer. Okay, so current layer means this one. So now that's why we have 3 input and 3 output, because bias is not affected over here, that's why here. Okay, now similarly this set of weights between hidden layer and the output layer represented by 2 cross 4, because you see I have 2 output layers, that's why 2 row, and 4 input layer, 4 layers from the hidden side, right? 3 are new input and 3 are neuron and 1 is bias, so that's why 4 are the uh, I mean, their number of columns is 4. So in this way you can actually initialize 2 matrices which are representing the weights, synaptic weight between input and hidden and output layer. Fine. Now you see, similarly we can, I mean, we can store the output of this neural network as output vector, something like 0.35 and 0.52 that we have seen, and the error vector will be something like this, right? So from here your job starts. So let's see. So as we have seen the forward parts, just you see, if you know, if you, if you want to, before you understand what actually is happening, we have to you have to remember this set of steps, because this is what we are going to calculate with respect to a matrix, so that the entire computation becomes very much easier and straightforward. So first thing we have to calculate del k, then del j, and like this. So you see, in a similar way we have calculated this one. So first thing is that hidden layer output calculation is a forward pass I'm doing. Okay, forward pass means that this is the, synaptic weight matrix will be multiplied by this set of inputs, and we'll get this one. This is the actual summer value. So this is the v, and then this is the y, will be get something like this, right? So this is my activation function. Then for the same thing, now we have, we will find out the output of output output from the output layer. So same thing, that v1 v2 will be, you will be equal to what, will be equal to this one into something like this. So this is your 4 v's. Okay, this is, equal to something like, this is the 2v of the output layer, which will be go through the activation function, will ultimately y1 y2 become 0.663 and 690. So anyway, so actually if you calculate it, so we will get 0.663 and 690 in the output layer. So that means just what we were discussing here, it was an arbitrary value. So if you actually calculate it, it will become 0.663 and it will become 0.690, that we have seen, right? So now what we are expecting? We are expecting that this should be 0.98 and 0.01. That means this is the error. So error the error will be equal to 0.99 minus this one and 0.01 minus 0.690, right? So from here this error calculation starts. You see there are e1 equal to e1 e2 vector. As a vector, if you consider, it will be equal to something like this. So your error is like this. Now your delta calculation starts. The output layer delta calculation that we have seen. What we have seen over here, the it was something like the output into 1 minus output into summation for or delta k into wkj, and this part actually we can easily compute by the matrix. I'm sorry, this is for delta j, but I have to calculate delta k first. So this one we have to calculate first. How we have done, you see, it is just a simple matrix multiplication by which you can go through the finding these deltas. So these are actually delta k, I mean delta for the output layer. And you see this dramatic multiplication. This is nothing but the error. I'm sorry, this is not error. This is actually the output. Why? Output into 1 minus output, right? Just like what was there. 5vj means actually yj. I'm sorry, 5vk into 1 minus 5vk. So 5vk means actually yk, right? So yk into 1 minus yk into the error for particular delta k, right? And with this matrix, actually what I have done, I have calculated all the data at a time. You don't need to go for any for loop for del ik equal to 1 to 0, then calculate for delta 1, delta I. I am calculating from with respect to matrix, so that actually you are calculating, I am calculating at a time all the deltas of the output layer. And this is the benefit of using this. And second thing is that it become very easy to compute, to realize. So as soon as your output layer delta calculation done, now you can compute hidden layer delta calculation that we have seen. Now you see, in case of hidden layer calculation, you have seen it was 5vj into 1 minus 5vj into summation over delta k into the wkj. So this part we can use a matrix directly because I have this delta as a vector. You can easily multiply this vector with this matrix if the dimension, if you are able to match the dimension properly. And similar thing over here. So you see, basically what I have done, this is what your here I have three deltas naturally because I have three neurons in the hidden layer. Bias is, we obviously bias we will not consider, and this is what the part of the synaptic weights, that is the wkj, which are connected, you see this one, which are connected with the output layer, because that is required, right? Wkj, the synaptic weight between hidden layer and output layer. So this wkj is multiplied with this delta k. You see, this is the delta just we have got. This delta I have multiplied into phi of vj into 1 minus phi of vj. Sorry, phi of vj into 1 minus phi of vj. What is phi of vj? Phi of vj means yj. So yj we have just got it in the previous case. You see this one, yj, right, for all y. And so you see, with this set of matrix multiplication, simple matrix multiplication, we are able to find all the delta of hidden layer directly at a same point of time. As soon as this delta we have got, now it become, it's very easy to find the delta w, because it is now again a simple play, simple play of a matrix multiplication. We've just multiplied delta with this y, we have got this because that is required, right? Because ultimately, with respect to the equation, you see delta wkj is, uh, I mean, learning rate into the delta k into yj. Similarly, delta wji is learning rate into delta a into xi. So that is what actually I have written. Okay, we are computing this change of weights w delta w. But by the way, I don't know whether, yes, there was a mistake, a very simple mistake, that is I should I should multiply with a scalar value that represents that eta. Generally, value of eta varies from 0.001 to 0.05. So this particular value should be multiplied with a eta. That is left, that I have forgotten to write over here. You can do that. So you see, again in the same way, the synaptic weights, the change of synaptic weights between hidden layer and output layer will be simple mathematical, simple matrix multiplication. So basically the set of steps that I have shown you in my previous lecture is nothing but actually series of matrix multiplications. So if you are able to realize it, maybe it will take couple of minutes to write a learning program, learning algorithm, implement a learning algorithm, right? So as soon as you will able to get this delta W for different layers, you can easily now calculate these new weights. So initially my weight was something like this in the output layer, I mean in between hidden and output layer. We have got this delta W as something like this. If you just add it, I will get a new weight. Similarly, the set of weights between the synaptic weights between hidden input to hidden will be something like this. So that means the new set of weights will become, initially it was like this, that will now change to the weight something like this. And now the next pattern you are going to fit, and again it will finally go through the set of outputs. uh, Depends on that, some error will be calculated, and ultimately again the weight will change. Now one thing you see, that here we have some negative value in the weight, so that's why I told you that, you see, it is not possible to restrict the set of weights to some certain range, and that is a actually very innovative point of the multi-layer perceptron, is that whatever initial weight you put, the multi-layer perceptron is capable enough to optimize its weights such that it finally produce the correct output that actually is the desired one. Okay, so that in that case there is no limit of these values of these synaptic weights. It can be say 10, 20, 0.0075, or maybe minus 20. It's, I mean, that the final value of the synaptic weights doesn't depend on the initial value of the synaptic weights. And that is a most interesting point of this learning, I mean of the multi-layer perceptron or the neural network structure. So I mean this is a very simple example we have discussed over here, but I mean in this way actually a learning happen. Now question is that it's not everything about the learning we have discussed, but something about the preparation of the data is left, that we will go for in the next class. Okay, so we will see that actually that there is something left in part in the during the learning part, that there are some cases where we have to optimize uh, the weights in much more better way, so that it can actually identify the points in a generic way. That is what we actually do through the form of what we call regularization. So this particular we will start from this point from the next class. Okay, thank you.